So before we start, I just wanted to mention a couple of things. One is that yesterday, or rather in the Monday's lecture, we were discussing about the quiz submission. So what I've decided to do is that we will continue to, I'll continue to upload the quiz. Okay. I'll obviously put the deadline, but what you can do is you can submit the quiz whenever you are finishing, right? So we will not, look at the late submission for the quiz. So as long as you have submitted the quiz at some point, it's okay, right? So we'll still continue to have 5 marks for the quiz submission and 5 marks for the attendance. But the 5 marks for the quiz submission, we will not look at whether you have submitted late or on time. Okay. So I'll give you the leisure time as to when you can finish the quiz. For the lab submission, obviously we have the strict deadline, right? And you will have to follow that. For the late submission for the quiz, I was discussing with TAs, and we do have a scheme that we were thinking that we will be implementing for the late submission. So if you are, let's say, late by, let's say 12 hours, or if you are late by a day, or if you are late by 3 days, then there will be some deduction of the marks, because we cannot have the same marks given to the person who submitted on time the lab assignments, or the person who submitted like 2 days late, right? So we will implement that policy, and I will share that policy with you in Moodle. Okay. So that is how we will go about this one. So we'll continue to do the quiz, but I'll give you the time, so we will not deduct any marks for the late submission there. Okay. That is how we will do it.
And so will that be applied to from quiz 3 or from quiz 4?
All the quizzes. Okay, all the quizzes, right? We will implement it similarly for all the quizzes. So I'll not say that only from quiz 3 or quiz 2 or quiz. I mean, all the quizzes. If you have submitted late, it's okay. The purpose for the quiz is for you to learn the topic, not following the deadline, right? For the lab, yes, you do need to submit on time. If you are late, it's still okay, but we will deduct some mark from there. Okay. So for the late submission for the labs, there will be some marks deduction from what you normally get, but for the quiz, we will not do that. Okay. All right. So let me continue. If you have any questions from the previous lecture, I can take them, or else we can continue with the current topic that we want to cover today, right? So any questions from the previous lecture about the GCC steps, or about the library files? How do you create library files, and what are the difference between static and dynamic library, and so on? Any questions? All right. So if no questions, today we are going to cover a topic which also falls in the similar area, and that is called make utility. Okay. So make is the utility provided to us again by the Unix based operating system. And this is the link where you can go and look for more information on the make. You also have the man pages for make, where a lot of information is given. What is the purpose of make, right? So that is the question first, right? So why are we learning this? So what happens is that when you develop any software, right, a software will not have a single file or a small piece of code. Usually in our assignments, in the lab assignments, or even during the course, we do create some reasonable size software. But when you go into the industry, it will become larger and larger, because usually the software products are not like 100 lines code, right? It will be thousands of line codes, if not lakhs of lines of code, right? So the point is that obviously you modularize your software, meaning that you create different files, right? You may have several header files, you may have several C files, and then there may be interdependencies between those C and header files, right? So some functions defined in one C file are being called from another, and so on, right? Also, there could be multiple GCC commands that you will have to execute because there are interdependencies of the C files. It may be possible that you are creating the library files as an intermediate functionality, and then you are using that library file to generate your executable files at some point in the project, right? So what I'm trying to say is that, you know, the projects, when you build a large project, it's not going to be few files, right? It's not going to be a small number of files. It's going to be large number of files. So how do you manage such large project? Okay, that is where the make utility comes handy. Okay, so there are first two problems we have to solve using make. So first problem is that we know that whenever we have some source file, so this is just some source files which I've shared here, but that source file is available in your code files. So let's say you have a hello make.c is one of the C files which has a main function, which is then calling some function which is available in your hello func.c, right, which is where your function is. And then you also have the header file, which is where you are declaring your your forward declaration of the functions, and maybe you have some variables also you are defining. So obviously I've just used these three files for now, right? But I wanted to show you that how can we create the make utility script for compilation of these three, right? And then we will go more, we'll go more advanced in the make file, right? So first of all, we know that when you have these three files, the simplest way to compile this is just run this one GCC command, right? What is that GCC command? That GCC command says that you create an executable file, and you have these two source files which you are using, right, from which you compile, and then wherever there is a main function, using that you will be creating your executable file. So this is a simple GCC line that we normally execute. Okay. Now, one of the challenge that we have with the larger project is there could be many such commands that you may have to execute. Now, if you, let's say, give a project to somebody else, like for example, when you install a tool, right, a new tool, let's say if you install a Python on your computer, right? Now, Python is not a 10-line code or 10-file code, right? It has hundreds of files. Okay, how do you compile that? So what you have to do is you have to give those commands in a script format, and user just needs to run the script, and that script is what we call a make script. Okay, so one problem that we are trying to solve is that we don't have to remember all the commands that we want to execute. Okay, that is one problem that we are trying to solve. Okay, and you can just give the script to somebody else, and you just tell them to run the script using this make utility, and that will take care of all the project building, right, the compilations process. The second thing that we are trying to solve is, let's say if you have 100 files, and during the project work, let's say you are only modifying 10 of them. Now, you don't want to recompile all the 100 files, even though there are only 10 files which are modified, right? So you want to make sure that you only recompile those files which are modified only, right? You don't want all the 100 files to be recompiled, because you are wasting time, right? I mean, the compilation of 100 files will take more time than the compilation of 10 files, obviously. So you don't want to recompile all the files. So you take help from the make utility, which will check that which files have already been compiled earlier and doesn't require to be recompiled again. Okay, so that is another advantage of the make utility that you can use for. There are many other advantages of the make, and as we learn more and more, you will come to know about it. So first, we will just go with a simple make file, and that simple make file is what my make file 1 is. So these two files, these two source files, right, is what is going to be used to build our executable file, right? So this is basically the make script, right? So in the make script, you first have this first line over here, and in this first line you provide the target, right, the target output that you want to generate, and you provide the dependencies for that target. So basically what you are saying in this line to the make utility is that my target is hello make.out. That is the executable file that I want to generate, and which files are required for generating this output, this executable file, are these two C files. Now, as you can see, I have not provided the header file here because the header file is already included in in this C file. So the pre-processing step will take care of that, right? So once you specify that what are the dependencies and then what is your target, then underneath that you provide the GCC command, right? So what make utility will do, it will check whether the date and time for both of these C files, right, are newer than my target, right? Meaning that I want to check whether the executable file is the most current file or not, right? If it is a current file, then you don't need to actually run this command, because by default what will happen is when you run this command, always this files will be compiled and the new executable will be created every time, right? Every time new executable will be created. But if you use a make utility will make sure to check the date and time for both of these dependent files, right? Both of these files on which my executable is dependent upon, and it will check whether any of those files have been modified or not after the earlier version of the executable was created. If it is not modified, right, then it will not actually run this GCC step because there is no need to do anything. Okay, so what we will do is first we will actually okay, so first let me show you how do we actually run, sorry, how do we run the make utility, right? So to run the make utility, you will notice that in the instruction in the manual page, it is saying that the script that you want to create for the make utility has to be in a file called make file. So make file is what you need to create, and you need to put this particular script that I have put into a file called make file. Okay, and then once you have that script in the make file, all you do is just run make. When you run make, it will search for the file name called make file, and whatever commands that you have provided in that make file, it will be executed. Okay, so let me copy make file 1 into make file. Okay, and let me first remove the executable file if it exists. I don't know whether it's there or not, but I will remove it so that the recompilation step is taken care. Okay, now if you look at my make file, the make file contains the make script which I have shown you, right, on the Notepad++. So I'm going to just run make, and that's it. So when I just run this make utility, it will look for a file name called make file in my current directory, and it will take care of these commands. Now it will find out that the target does not exist right now. Since the target does not exist, it will definitely know that these files will have to be recompiled and the executable will have to be made, right, or created. So let me run that. So when I run make, you can see that it executed this particular line because it found out that the executable did not exist earlier, right? So it has to be recompiled and it has to be created. So when you do ls-ltr, you will see that hello make.out is created. Okay, but now let me run the make again. If I run the make again, now what happens? Now your executable file is already a most current executable file, meaning that the date and time of executable file is newer than your source file date and time. right? So therefore, there is no need to do the recompilation. There is no need to run the GCC command again. That is what the make utility will check, and it will skip the running of GCC. Okay, so you saved the time of the computer by not rerunning your GCC command. Now you will say that it hardly took some time to run the GCC. Yes, our files are smaller. We have fewer files. So for this kind of work, it may be okay. But when you have very large files, more number of files, every microsecond counts, right? Every microsecond counts. Okay, so you can see that it basically, the make utility checked that my executable file is up to date, meaning that it has a newer current date and time compared to the source on which it is dependent upon, right? So therefore, it did not run the GCC command. So the make utility gives you two advantage. One is that it will only run the command if the executable file is not there, or if the executable file is older than the source on which it depends upon, right? So and then it is saving the you are also able to save the command. So the user who is going to be building the project just has to remember to just run this make, and that's it. That person doesn't have to do anything because you have already provided the make file. Okay. Now the question is that if you have multiple make files like we have, okay, and you can't call every make file script as a make file, what do you do about that? Okay, so the make utility gives an option or switch which is called -f. Okay, so -f switch allows us to actually run the make file script from any file name, right? From any name of the file. It basically, instead of looking for a default make file, you are actually providing the file name by using the -f switch. Okay, so I can actually say make file 1 here, and when I do that, now make is not going to look for the default make file name, but it is going to say that whatever script that is provided in this make file 1 file, that is what I'm going to run. Okay, and that is what it will do. And again, it did the same thing, right? So this is another option you have. So therefore, you can actually create multiple versions or multiple make files in your current directory, and depending on which one you want to run, you can just provide this -f switch in order to run them. Any questions so far? Yes. So Krupal, we can definitely have multiple make files in the subdirectories. It is possible.
Sir, when we provide.
Sorry.
Sir, when we provide only make command, it will run all the. It will search for all the make files. Like if we have multiple make files, then it will run all the make files.
No. So what you have to do is that once you can change the directory in your make file using the cd command, and then you can run another make.
Okay, sir.
From within the make file. Okay, so you can kind of run recursive make. There is also a switch for recursive make. I believe it is called -r. No, it's not -r. I'll look for it, but basically it is the switch that is also available to you, which allows you to run the make file recursively. Was it -m or some? There was one switch, and I don't exactly remember that switch, but there is a switch which allows you to run the make file recursively. But in any case, even if you don't run it using that recursive switch, you can basically you can use the make inside this script, and then you can run another make if you want to, right? In fact, if you have installed any, if you download any source of a very large project, for example, if you download the source code for Python, or if you download a source code of any operating system, you will definitely be able to see how the recursive make files are being used, because definitely, your operating system, your Python, the person who wrote Python language, right? That is what I'm talking about. These are very large projects, and they have various make files in various directories and subdirectories. So again, I can give you the basic understanding or basic introduction to these topics. And if you are more interested in such topics, then you should dig in, right? I mean, you should dig in more into that particular topic, right? So this is how your basic make works. But what is the problem with this make? The problem with this make is, even if I modify one of the C files, so let's say, for example, let me change this to 1 so that I can modify this C file, right? The make hello make.c. Even if I modify this one make file, what will happen is that when I run my make, right? When I run my make, it will still have to recompile both these C files, because I have not mentioned that which C files have been modified and which C files should be only recompiled, okay, for creating a new executable file. So whenever I modify any one of these C files, it will again recompile both of them, and it will create a new executable file. That again is a problem for me, because it is wasting the CPU time or the computer's time. Okay, so what is it that I can do, right? So I need to somehow separate out the compilation part with the creation of the execution, which is in the linking step. So the linking step is to be identified and separated out from the compilation step. So, when I say compilation, I mean to say the first 3 steps, right? Pre-processing, compilation, assembling, all the 3. So creation of the object file is what I mean to say. Okay, so what we will do is we will create another version of the make file, which is this one, and this version of the make file will then do that process for us. Now, there are some standard variables also with make that you can use. One is called cc, where you can provide the compiler which you are going to use for your programs or for compilation steps or linking steps. You can also use flags such as C flags. So why are we using this variable? This is basically saying that compilation flags, right? C flag stands for compilation flags. And what we are doing here is we are saying that -i switch for the GCC says where to look for the header files. Okay, if you look at this one also, it has this hard-coded value -i dot, meaning that look for the header files in the current directory. That is what we are trying to say. Okay, so same thing we want to do here. Look for the header files in the current directory. That is what we want to say. Okay, so we are going to now. So once we declare these 2 variables, we can use those variables using this syntax, $ in parenthesis the variable name. Okay, so that will basically substitute the value of the variable here. Now, for this line, we are saying that we want to create an executable file which is called hello make. Okay, I didn't provide out here, but you can do that. So name doesn't matter, right? This is the target we want to create. And what we said is that for this particular target, the dependent files are not the C files, but the dependent files are the object files. So object files are dependent for are the dependencies for this executable file. That is what we are saying to make utility. So now the make will only check for the date and time for the object files compared to my executable. If both the object files are older than the executable, then it will not run this step. Okay, but then the question is, who will check for the date and time of the object file compared to the source files? And our GCC compiler is smart. Okay, our GCC compiler is smart, and it will check that in order to create the object file, if the object file has a newer date and time compared to the C file, equivalent C file, then you don't need to do the compilation step. Okay, but if the object file is older, then it will do the compilation step for that particular object file only. Okay, so in other words, we took help from the make utility to do the linking step, and then the GCC compiler, right? The GCC compiler will take care of creation of the object file depending on whether the source file has been modified or not. Okay, so what I will do is I will actually delete the object file first, right? I don't know if it's there or not. So hello world.o, let me delete it, and then hello func.o. So both these object files have been deleted, right? And now I'm going to run make file 2.
So it won't be hello make.o.
Sorry. Thank you. Thank you. Now I'm going to run make -f make file 2. Right. So this is my make file. This is my current make file. And now you will see that when I did that, right, when I run my script here, it is doing the compilation step for the hello make.c. It is also doing the compilation step separately for hello func.c, and then finally it is doing the linking step. So the make file understood that the objects are needed, and it told GCC compiler that the object files are needed, and the GCC found out that object files are not there, so therefore I need to recompile these files, and it recompiled those files individually, and then it finally told make file to run this GCC command. Okay, now the question is, let's say if we just modify one of the files, what happens then, right? So again, I'm just going to modify, let's say make file, the hello make.c, right? And let me just change this to 0 again. So that means I'm just modifying the hello make.c, just that one C file. Okay, now what the make file will do, again, it will ask GCC to run the linking step, but then the GCC will compare the date and time of my C file compared to the respective object files, and it will find that the hello func.c is older than hello func.o, but hello make.c is newer than hello make.o, and therefore there is a need to run the compilation step only for hello make.c, and that is what it will do, right? And then it will finally do the linking step. So again, I'll run the same make file, and you notice that it is only doing compilation for hello make.c, and then finally do the linking step. Okay, so in other words, in this make file, by putting the object file as a dependencies for the executable, we sort of separated out the steps for the compilation part and the linking part. Okay, so we solved two problems, right? We save the commands, and the commands are there in the make script, and then we ensure that only the C file which are modified will need to be recompiled, otherwise not. But there's still one more problem here. If I modify the header file, does the make script recompiles the required C files? No, it does not. It does not. Why? Because when you look at the make file, there is no reference to the header file here. And so the make file doesn't actually know that the header file has been modified, and therefore it requires the object files to be regenerated. Okay, so when I modify this header file, and if I run this, you can see that it still says that hello make is up to date. Okay, because even though header file is modified, make does not know about it. because we have not specified the dependency for the header file for the executable file as a header file, right? So we come to the third makefile. Okay, we come to the third makefile. So what is this makefile doing? Now we are going to be putting the header file also as a dependency for the compilation steps. Okay, so again we define our declare our two variables, cc and cflags. We also declare one more variable called deps, and deps is where we provide the list of header files. Okay, and then obj is another variable which we are creating for the object files. Again, if you can create this or you may not want to create it, it's up to you. Okay, you can directly put these files here like we did earlier, and that is also fine. Okay, or you can directly put the include file here, that is also fine. Okay, but I just wanted to show you that how you can create more dynamic versions of the different makefiles. So that's why I'm kind of incrementally making the makefiles advanced, right, or more complex. So now what you can do is you can see that what is the target here, right? So my target is saying that wildcard %sign .o file, and my dependent files are the same .c files, right? So whatever the name of the .c file has to match with the .o file using this wildcard. In addition, I'm saying that the dependency is also with the header file. Now you may say that the header file is only used in, let's say, hello make.c, not in hello func.c. Yes, you are correct. And in that case, you will have to then again separate this line out into two more lines, right? Or one more line. So here you can just compile the hello make in this particular make script, and in the next set of make script you can just compile the hello func without using the header file as a dependency. Okay, so you can do that again, but I'm just giving you the idea as to how to use the header file as a dependency here. Okay, so here what it will do is, also I wanted to show you this wildcard thing, right? So what it will do is, for each of the source files that it finds, it's going to create a object file, right? It's going to create an object file, and it will consider that this header file is also a dependent header file. So which means that whenever I modify the header file, also the make file will now notice that for each of the object file, the header file is also a dependent file. And therefore, if the header file has a newer date and time, it will recompile all the C files into the newer .o files. Okay. Now, how do we do the compilation step? The compilation step is done using the -c switch, right? We know that. Okay. I'll come to this particular switch a little bit later. So -c switch is for the compilation. We know what the -o stands for. -o is for the output file. Now here you could have multiple output files, right? Because for each of the C files, you could have a different object file, right? Depending on what is the C file name. So what we do is that we use this particular variable. It's also a special variable called $about. What this variable says is that pick the target from the left side here. So for each of the command, take the target from the left side here and replace it over here. Replace it over here. Okay. This particular command, this particular variable $, says that pick only one of those C files, not all of the C files, right? So less than basically says pick one C file equivalent to that O file. Okay. Pick one C file that is equivalent to that O file, and in addition, use this header file as a dependency, right? So the less than sign is to pick only one of the files, not all of the C files. That is what we are doing here. Okay, and then $C flags is again there, up here. Now, what is this -save temps? Now we know that whenever we run GCC with -c switch, it performs three steps: preprocessing, compilation, and assembling. But when you look at the final output, you will only see .o file created, even though internally .i file is also created and .s file is also created, but those files are not saved. They are only maintained in the memory, in the RAM, right? And then once the .o file is created, those files are actually removed, right? The temporary files that are created in the memory, they are removed. But let's say if you want to actually retain those files, you want to keep those files, right? You can use this option. So you can say that minus save temps, which means that whatever the temporary files, the intermediate files that you are creating, which are .i file and .s file, also keep them because I want to see them. Okay, so we ran individual steps earlier in this chapter. We ran the separate preprocessor, we ran the separate compiler, we ran the separate assembler. If you don't want to do that, if you just want actually all the files to be saved, right, and you want GCC to do all those steps and save all those files for you, you can use this particular switch, save temps. Okay, so this is how the compilation steps will go, and then you finally do your linking step. Okay, so in the linking step, these are your dependencies, which are your object files, right? And then again, you use the $about sign, or you can also use directly make here, hello make here. It doesn't matter because you only have one target, so it doesn't matter. Here we are using $caret, not $less than, because we are saying that whatever number of object files that you have, all of them has to be used over here, not one of them. So less than sign allows you to only pick the first, to pick one of those files, whereas here the caret will allow you to pick all of those files. Okay, so that is the difference between these special variables that we use. Okay, so when we run this script, now we are informing make utility that your header file also is a dependent file for your for creation of the object files. Okay, so again, when I run this one, make -f make file 3. Right now, what it did is it again recompiled both the files because I had modified the header file, right? Because I didn't modify the C file, but I modified the header file, and therefore it recompiled both of these C files again, right? And it created the .o file, and then finally it also created the linker. It also finally created executable using those. Now the save temps are used in these steps. So if you look at ls-ltr, you would notice that the .i file is also created, .s file is also created for both of these programs, both of these C files, right? So if you want to see what is the assembly code for hello make, what is the assembly code for hello func.c, all of that you will be able to see it here. Okay, so again, you don't have to use hello save temps switch, but I'm just showing you the purpose of that, right? Why we need to use it. Any questions so far? Am I still audible?
Yes, sir.
Okay, all right. Just want to make sure you are not at sleep.
Sir, these commands like save temp and all which you have written, are they available in main file or somewhere? Like
Yes. So that you will be able to find in the GCC. So if you do man GCC, then -save. Let me hide this guy. Save temps. Okay, -save temps stores the usual temporary intermediate files permanently.
Okay, sir.
Okay, so you'll be able to find those information in the GCC manual page. So like I said, these things are manual pages are very expensive, and they have a lot of information there. That's why sometimes it is difficult to actually look for a particular information, but at least from the slides you will be able to get some idea about that. And then if you want to know more about it, you can go through the manual pages. Or you can search in the Google, and then once you find that switch in the Google, then you can search then you can look for that in the manual pages. Either way. Yes.
Sir, actually, I saw this slide. I think my doubt will be clear up.
Sorry, I didn't catch you.
Sir, I think you will address this thing later because I saw this slide. So I was asking the same doubt. If we had different folders, then what we had to do?
Yeah. So I have this I have this project version, small project, of course, but so what we have is we have a project, let's say, right, and then you have a folder structure for a particular project. And so if you look at the code files that I've provided you, there's a folder called makefile. Under the makefile, you have these folders: bin, include, lib, source. Under the source, I've created obj, right, and so on. Now, what we are looking at is obviously in the Windows folder. But if you want to do the same thing in Ubuntu, there is a command called tree. Okay, what the tree command does, it provides you the tree structure of the directory where you are in. So for example, let me go to make proj, and then I will do tree, tree, enter. Now you can see that it provides me the complete tree structure, and it also includes all the files that are there in the tree structure, right? So it's giving me the file names as well as the directory names. If you only want to see the directory structure, then so it says you have 5 directories and then you have 19 files, and these are all the things, right? But if you just want to see the directory structure, you can just use -d switch, which will then only give you the directory structure. That's all, right? So it's telling me that I have a bin directory, include directory, lib directory, source, and obj. Okay. So now what I want to do is that when I create a object file, I want to actually put it here, right? I want to put all my includes over here. When I create a library file, I want to put it here. My executables, I want to put it here, and so on, right? All my source file, make files are going to be in the source directory, and so on. So how do I take care of that? Right? That is my next version of the make file. So I'm basically incrementally making the make files complex so that you understand, how exactly the progression of the make files usually work. So you include your I directory. IDIR is a variable that I have called, which is what the path to the include folder is. Now, generally speaking, we want to use the relative path, okay, instead of a absolute path, because see what will happen is that if you provide this make file to someone else, right, they may not create directory structure exactly what you have in the starting from the root of the drive, right? So for example, your structure could be C my proj something. Somebody else might be using D drive, or maybe under D drive they may have a subfolder where they are putting your this project, right? So if you use the absolute path, it will be difficult. It will not be able to compile. So they'll have to modify these make files. So instead of that, what we do is we provide a relative path, okay? And the relative path is, you have to look at it from where the make file, where you place the make file. So make file 4 is placed in the source folder. So if you look at the source folder, this is where my make file is, make file 4. So all the path that you provide in the make file will be relative to the source folder. That is what we have to do, right? So we now say that dot, which is your parent directory. So from the source, you go to the parent directory, which is my make project, and under make project there is an include folder. Okay, so that is what I specify in the IDIR. Again, my usual two variables. Okay, and now here I'm saying that where to look for the include file, which is not a dot, but it is my IDIR. I also have the object directory where all my object files are going to be. Now you can see that I just specified obj because this is the child folder into the source. Another way you can specify is current directory /. So this also will work, but if you don't provide this, just providing obj will also work because it is the child directory of the current directory, which is the source folder. Then your lib directory. Let's say if you are using standard library files or even your own library files which you have configured with this -l switch, right? You are creating a dynamic library file, and that dynamic library file is accessible using this -l switch, and you want to access that, you can create some another variable called libs where you can put all the library files that you want to access. Okay. Now we come to the dependencies, right, for the header files. So for the header file dependencies, we know that if you have a list of header files, right? So for all those header files, either one option is you can do like this, right? And then let's say another header file, something like this, right? Whatever that header file is. Okay, you can do like this. But that means every time you will have to, pad this or prefix this ../include. We don't want to do that, right? Because why then there is a need to declare this variable? There is no need, right? So one thing that we can do is we can either rely on this C flags, okay? But then the other option is doing this pattern substitution. So this is the pattern substitution command that is also available in your make script. And what you can do is you can say that all the dependencies that you have, all the header files that you have, you want to prefix that header file with whatever the value is there in this variable. Okay. So what this command is doing, it is basically creating, right, a path with the header file name in my new variable called deps. So deps now will actually contain .. /include and header file, whatever number of header files you have. So this is another option that you can use. Okay. Why we are learning this? Because anyway, that will be needed for the object files. So we are doing the same thing for the object file. So for object file, I have _obj as a variable where I have just mentioned the object files. And then I'm using the pattern substitution to just, prefix the folder, right, obj folder in front of each of these obj files. Okay, so this is what my variable declarations are going to be, or variable creations are going to be. Now I come to the actual compilation and the linking step. So the compilation is done same way as we have done earlier, no change except for the folder. Okay, except for this folder. That's it, right? Because we have to provide here %o, and %o, if you don't provide the obj directory, then it will create it in the current directory, which is the source directory, right? So you have to provide this path to create the object file in the obj directory. And then this $obj is then going to be using this particular object list, object file list, and that will be again in the obj directory .o files, and it will create your executable files. Okay, so this is how you will be able to create your executable file using the folder structure. Okay, now there's one more thing that we need to learn about makefile. Now, many a times it will happen that you want to run some, shell commands or terminal window commands, right, in your make script, apart from the compilation steps or linking steps and things like that, right? So, for example, you want to clean up your project. You want to say that I want to delete all the temporary I want to delete all the temporary files, right? Let's say .i file, .s file, .o file, even the executable you want to remove. Maybe you want to remove the library files, right? So let's say you want to build your project from scratch, clean, right? Clean project building that you want to do, right? So you need to figure out how to delete all those temporary files. You can't expect a user to remember all those temporary files and how to delete them. You have to provide that information or those instructions in your makefile itself. So what we can do is that instead of creating a label as a target file, okay, we create a label, something like this. So clean is a label, right? It is a label, but it is a label without the target file, right? So this clean is not saying that this is the file I want to create, right? So this target is not a file. This target is just a label, a dummy label, right? Whereas here you can see that this is not a dummy label. It is actually the target, which is a file. Here the target is a file, right? So you can have two types of labels in Make. One, which is the actual target, which is a file, or you have a target which is a label, dummy label. And in order to indicate that it is a dummy label and not the actual target file, we use this special label called .phony. Okay, why we are doing this? Why we need to provide this information? Because it may be possible that the actual that this directory where your make file is, maybe there is a file name called clean, maybe, right? If there is a file name called clean, we don't want make to get confused about the target as file name or target as a label. So by specifying this .phony, right, this is the reserved word. This is the reserved word of make, right? You always have to specify it like this, .phony. So we are saying that this is the phony label or a dummy label, right? So using this, we are saying that this is the dummy label that we want, and that dummy label is what it is going to do. It is going to do these things. So you can see that by providing this clean label, I'm actually writing this remove commands, right? And we can delete all the temporary files that we want to delete from the folder, different folders, right? And that is what you can do. So this is another way of making sure that you can actually run different things with single make file, right? So you can actually run the clean part, and also you can run this other executable part. So let us do that. So let me first run the regular make so that it creates the obj files and things like that. I need to go to the source directory. Make -f, make file 4. Okay, so it created all the files that I require in a specific directory. So you can see it created the .o files in the obj directory, and then it used those files and then created the executables in my current directory. So if I look at this, so I didn't prefix the executable with bin directory. So actually it has been created here, but I could change my make file to put it in the bin directory. So I can actually say /bin / right, and then same thing I can do here, /bin / and now it should actually create it in the bin folder. So let me just remove hello make from here. Okay, so now it just did the linking step because the objects were already there and it couldn't find the hello make in the bin folder, so it just did the linking step, right? So that is what you can do with the make file. So now your folder structure, if you see it, you will have all those required files that you want. So if you go under source, under obj, you will have those obj files. If you go back and look at the bin folder, you will have the binary file and so on, right? Now, if you want to clean these files, these executable files, object files, and so on, you have to use that clean label. So how do we use the label with the makefile? All we do is provide the label name here. So we can say that instead of running the default target, right? So the default target will be to create object file and executable file. That is my default target because that is at the top. So whatever is at the top, that is what it will continue to run. But then it will stop at the executable file. Now we want to actually only run the clean part, right? We don't want to create my executable. So I can provide the label here. So when I provide the label here, I'm basically telling the make that don't run anything else but whatever is mentioned in this label, in this clean label. Okay, and that is what it will run. So when I run this now, it is only going to run these remove commands. Okay, and now if I go back and look at the directories, you will see that those files are gone. Right, those files are gone because I removed them. Okay, so this is how you can actually use the labels and do other things other than the building of the files. Any questions? Okay, one more thing, one more advanced stuff that I want to look at is let's say here in this particular makefile, we said that we want to create this executable, and this executable is dependent on this object files, and therefore the object files are also being built, right? So there is only one final target that we have, and because of that, it is basically checking. The make is checking that this for generation of the target, I require this obj files, and therefore I need to run these commands as well by using this compilation. But there may be a need that in a single makefile, you want to generate multiple targets which are not dependent on each other. Let's say you want to create multiple executable files, or maybe you want to create multiple library files, or maybe you want to create a library file and an executable file, but then that library file is not really the library file which is being used by the executable or whatever. So what happens is that in make, by default, it only generates a single target, final single target. It does not generate multiple target files. So whichever is the first target that it finds, that is the target it will generate. Okay, but we want to create multiple targets in a single makefile. So how do we take care of that? So what we do is in this makefile, more or less the steps are similar. The only difference is I've also put the steps to create the library file. So let's say there is a library file which we want to create, and I've actually used the same codes that we have used earlier, and we know that this C file is actually using this library file. But in order to change the targets, what I've done is I've actually separated these object commands separately here. And because I've created this object command separately here, this line, even though it uses this lib obj, it doesn't know that this obj is actually the same as this one. So it actually, the makefile is considering this obj as separate than what is mentioned in this list. So this target is sort of, for the make, is different than what this target is. So what happens is that when this makefile runs, it only generates one of these obj file, which is the first target, and then it stops if I don't say what exactly I want to do. So let me just show you what I'm talking about. So let me first do make file 5 and then clean. Again, I have provided clean there, so we delete all the temporary stuff, and now I do make. Okay, now you see that when I do make, right, it is only executing this one thing, even though the other object files, the library files, and all of them are not there, right? But because of the way makefile is checking, it is assuming that this is the final target for me, and that is the only target it is going to generate. Okay, now how do I solve that problem? So what do? I basically create another phony label called all. Okay, I create another phony label called all. Okay, and I say that I want to use this phony label and say that all the files that I want to create, all the targets that I want to create as part of this make file. So the first target I want to generate is my SO file, the library file, and then the other target I want to generate is my .out file. And so when I do this, it's going to take care of creation of the SO file, right, which will then require the object file, which will then run these steps, and then finally it will also generate my executable file. Okay, so now in order to run this make file, I have to say all. Right, so when I say all, it will actually run all the targets which I have mentioned in the all label. Okay. Now we can see that since add.o was already created, it was not recreated again. Okay, but only the sub object file was created. Then using those two object files, it created the library file, then the compilation of my main file, and then the creation of the executable file. So this is how you would be able to use folder structure, the project folder structure for any large project using the make files. And you can control the compilation steps, you can control the linking step, you can control which targets will be built, you can control the dependencies of each target, and so on. So there are many things that you can do with make, and make script. So this is about make files, right? Any questions on the make files? No questions on the make files?
Sir, is there some sort of like helper or something out there? Like they just give that this switch does this command, this thing, or this command does this thing, like just short explanation.
So I'm sorry, I didn't catch you.
Means like you have got so many commands, so like you have to remember all those, or is there some sort of helping or short manual of 2-3 pages which may just tell in one line that this switch is doing this thing or something like that?
So see, I mean, you have you have two options or multiple options, I would say. One is looking at manual pages, right? So if you look at the manual pages, it will have all the switches and everything. But manual pages may have a lot more information sometimes than what maybe you want. I mean, if you know what specific thing that you want to do with make or GCC, what you can do is you can basically search on the internet, right? And many a times it will point to the somebody may have asked the same question maybe on the Stack Overflow or something, and so you will get an answer from there sometimes. So it's, I mean, I know there are a lot of commands with a lot of switches, and it's not always necessary that you remember all of them, but I think it's important that you at least when you look at the help pages, or when you look at some of those switches, I mean, what I'm showing you are the common things what people require to do in the make file, right? And these are some of the common ways you write the make file. If you want something more advanced than this one, maybe you have some functionality which is more advanced than this one, then you will have to research it out yourself. So you're talking about having like 2-3 pages of chichi, which only way I know is either you go to the make website, the GNU make website, where you will have information about the make tool, or you can look at the manual pages. Or if you want some specific instruction, like how do I do this, you can Google it out, and then somebody may have done something similar where you will find the ways of doing it, or switches that can do that. Any other questions?
Sir, is there any particular reason like the make files don't have any kind of extension or something? So like,
Well, there are extensions to make files. There is something called a CMake utility, which some people use. CMake utility, I think, is written in C. So you can write some of these instruction in C kind language. So I mean, see, basically, make files are the original ones, right? I mean, they were the ones which were created long time back. And on top of that, some people may have done some sort of an extension. And when you look at some of the larger projects, you may find that there are some people uses CMake along with make and something like that. But once you understand the basics about make, I think you would also be able to understand how these other scripts work. It's not very easy to understand those larger scripts because they have lots and lots of different commands, and some of the make scripts that I have seen, like for example, if you have time, we will do it later in the course, but you can actually rebuild the whole operating system. So you can actually download the operating system source, and you can actually compile, you can rebuild the whole operating system yourself, and then you can install that on your machine for some upgrade. So you can actually implement your own new system calls by doing that. So when you do that, you will have to download a complete source of Linux or Ubuntu, right? And when you do that, you will find that there is a big folder structure. In each of those folder structures, you have make files and stuff like that. So if you're interested in such things, at least what you can do is you can download the Linux source or Python source, and you can maybe try to dig into those make files and try to see what it does. Okay. All right. So what I'm going to do is I'm going to briefly start a new topic. I'll just give you the introduction for that one, since we still have a few more minutes, and then we'll do the majority of this chapter in the next lecture. So the next chapter that we are going to start is about file IO. Right. Now you may think that why we are learning file IO, because you may have already studied when you did your C programming course. And I agree with that. Part of this chapter you may have already studied in your C programming course. Okay. However, in the C programming course, what you may have studied is how to open a file, how to read from the file, how to write into the file, how to close file, and so on. Right. What we are also going to study here in this chapter is how the files are stored on the disk. What is the structure, right? So when a blank disk is given to you, right, how is the disk partitioned, or what are the different what are the different parts of the disk which keeps track of different files, what is the file structure, what is the directory structure, and so on, right? So Unix based operating system has a certain way of storing the files in the disk. And how do they do it, right? You may be opening the same file from the multiple programs. You may be opening the same file from the same program multiple times, right? So there are many things that you may be doing which without knowing it, but then operating system has to keep track of all those things, and it has to manage those files accordingly, right? So that is what again we are going to focus on. So files and directories in Unix based system. So in this slide, all I'm trying to show is a basic structure of your drive, right? How the drives are partitioned for creating the, for storing the data. So originally, there was a file system called UFS, Unified File System, where you only had one big disk, and the disk was divided into three parts. One is called super block, inodes, and the data blocks. So inodes are sort of like the pointers to the data block. So inode had an information about the file name, the access permission, the size of the files, and which data blocks are occupied by a particular file, and so on. Right? So it basically has an metadata information about the files and the directories. That is what the inodes are. Okay, and I'll come to very detailed about what inodes are later, but just to give you an idea. Then the BSD FFS was created by Berkeley University, and they created the cylinders. So now the disk is now divided into cylinders, and each cylinder has a cylinder group. So each of the cylinder group is something like this, right? And sorry. So they had an additional information about the block bitmap. What the block bitmap contains is that, let's say you have 1,000 data blocks here, right? Each of these data blocks are, let's say, of 2K size or 4K size, right? So each of the blocks are storing, let's say, 2 kilobyte of data or 4 kilobyte of data. So that is a configurable parameter in the operating system. So operating system decides that what will be the size of each data block. And so let's say in this particular disk, you have 1,000 data blocks. And what you will do is that for each of those data blocks, there will be a bit, a single bit in this block bitmap. Okay. And it will have the value of 0 or 1. If the value is 1, then you know that that data block is, let's say, available or is free, and it can be used by a file, right? That requires additional space. If the value is 0, then the data block is full. So this bitmap is nothing but a representation in the binary format that says which data block is free and which data block is not free. Similarly, you have an inode table here, and for each of those inode table entry, there will be a bitmap over here that says that which inode table entry is available, which inode table entry is not available. Then you go into the more advanced version of file system, which is called ext2. Now in the ext2, what they did is they actually divided. So cylinders were sort of like the horizontal division in the drive. So horizontal division in the drive was called cylinders. Now here you also have the cylinders are divided vertically. Okay, and you have block groups. So each of these cylinders are divided into sectors, what we call, right? So sectors are the division of the cylinders, and each of the sectors will have these block groups. Because see, what happened was that the size of the drives became larger and larger and larger and larger. So they had to figure out how to divide the drive in such a way so that we can actually access it quicker and faster and more efficiently, right? So this is how the ext2 version came into the picture. Now, for each of the block group, you can see that the format is exactly the same as it was here. Not much difference, right? It's almost same. ext3, it's again almost same as ext2, except for that it supports larger size of the disk drive and so on. In addition, it had this one additional feature called journal. Okay, so what this journal contains? So normally what happens is, let's say you want to write a data into a file. What we will have to do? The driver or the program which takes care of writing into the disk, right, which is what we call device driver for the disk. What it will have to do, it will have to go and search for that inode table entry for that file. It will then have to figure out that, okay, where that file starts here in the data block. It will traverse through all the data blocks till the last block. It will check if there is sufficient space in that last block where it wants to write the data, additional data or not. If not, then it will have to check that which data block is available to write additional information. It will allocate that data block for that particular inode, and then it will have to write the data. So you can see that there's a lot of process that has to go through, right? And it takes time. So in order to avoid that, for every single write, what they did is they created a temporary memory area in the disk, which is called cache or journal. So journal is nothing but like a cache kind of a area. So what will happen is that when file requires some additional writing, it will just dump it over here. And then in the background process, right, in the background process, it will try to figure out that where the space is available, and then it will be taken, the content will be taken from the journal and then actually be written in the file. Okay, so this is about ext3. ext4 and ext3 is almost identical except for the space and the size of the file and the disk that it supports, right? So here you can see that in the ext4 it supports up to 1 exabytes, whereas ext3 supported 32 terabyte of disk space. So maximum you could do 32 terabyte in ext3. In ext4 you are able to support disk size up to 1 exabytes. File size, you can go with 2 TB in ext3. In ext4 you can go up to 16 TB, right? And then the number of directory entries, right? The number of entries in the directories, you can go up to 32,000 in ext3 versus 64,000 in ext4. Okay, so this is the basic understanding of how the disks are divided, and how the different blocks or different parts of the disks are storing different kind of information, right? What is a super block? What is the inode? All of that, I'll come to that in the next lecture, right? Because we are at 9:48. Any questions? No questions? Okay. All right.
Sir,
Yeah.
sir, are these divisions on the hardware of the disk physically, or are these just logical partitions that is assumed by the operating system?
Okay. Good question. So basically, these are, when you say block groups, right? These are the physical divisions that are done, and then the logical partitions that are mounted, right? So in each of the groups, you will also have the logical part. So it is possible that in a single physical partition, you may have multiple logical partitions. Okay, or you can also have a single logical partition spanning across multiple physical partition. This information that you have is for each of the logical partition. So I'm assuming here that one group is one logical partition. Okay.
Okay, sir.
All right. Any other question? All right. So thanks everyone, and I'll
Thank you.
talk to you guys on Monday. Yeah. Any question? Okay. All right. Thanks everyone.
Thank you, sir.
Thank you.
So I wanted to ask, like, in the quiz, if we submit late, will that be allowed?
That's what I said in the beginning, that I will keep on updating the quiz on the Moodle, and you will submit, but we will not keep track of the time. So
Okay.
what we will do is we will still keep the 5 marks for the quiz, but it will not be compulsory to submit it before the deadline that I provide. As long as you have submitted, we will consider that.
Yeah, okay, sir. Thank you, sir.